Okay, in section 3.6 we looked at first order reactions. Now in 3.7 we're going to look at second order reactions. This is the integrated rate law for second order reactions. And my goal is that you're going to be able to use the integrated rate law for second order reactions to look at the relationship between the concentration and time, and also to look at half-life for second order reactions. So because the coefficient in this reaction is 1 for A, the rate is equal to the negative, because it's a reactant, change in the concentration of A over time. And we also know, because it's second order, that rate is going to equal K times the concentration of A to the second, right? This is the thing that tells us it's second order. Now, just like we did with first order, we can set those equal to each other and then use some calculus to integrate them. And when we do that, this is what we get. We get this equation, 1 over A equals 1 over A initial plus KT. Okay, so if I take that then and I rearrange it to just move these two things, right, I end up with it in the form of an equation for a line, y equals mx plus b form, right? With this being y, the slope being k, and time being my x, right? So a plot of 1 over a versus time gives us a straight line for second order reactions. So if we have a set of data and we are trying to determine if it's second order, and we have concentration given to us and time given to us, and you have a bunch of data points, you can try plotting 1 over a, just use Excel and create one more column for 1 over a, and plot time on the x, 1 over a on the y, and if you end up with a straight line, you have a second order reaction. And the slope of that will reveal itself. So let's take a look. What would the slope of this equation be? Take a second and go ahead and answer. Okay, so if you said it would be k, you were correct, because this is the mx term, k is the slope, t is the x, right? So the slope of this equation will be k. So let's take a look at second order reactions and half-life. So here's the equation that the integrated rate law for second order reactions. And we know that if we're talking about half-life, then the concentration at half-life is going to be the initial concentration divided by 2. And therefore, if we use that information, we can substitute this into the equation above. We'd substitute the concentration of A and put in the concentration of the initial A divided by 2. And we rearrange and solve for t. We combine like terms, rearrange, solve for t. This is what we get. So this is the equation for the half-life of a second order reaction. Okay. And you can see it's quite a bit different than the equation for the half-life of a first order reaction. First of all, if we had first order reaction and we're looking at half-life, you would, in the first half-life, you drop the concentration in half. In the second half-life, you drop it in half again. But that doesn't quite happen in the second order. In the second order, you might drop the first concentration in half. But then to drop it in half again, it's going to take a longer period of time. And that's because, unlike first order, in second order, concentration is a part of the half-life equation. And because it's in the denominator, it's going to increase this value. Okay? So let's take a look at zero order reactions. zero order reactions means that the reactant, so first of all, the concentration of that reactant does not affect rate. Doesn't matter how much we have in there, it's not going to change the rate of the reaction. Okay, so if we look at the equation, this is the rate equation for a zeroth order reaction, right? It's got an exponent of 0. And because anything to the 0 is equal to 1, the rate is just simply K. So if we look at this, rate's a constant. And if we wanted to look at what the plot of the concentration of A is versus time, we would get a straight line that looks like this. Okay? But what would a plot of rate versus time look like? Let's take a look. So the plot of rate versus time would be, now remember, the rate, in this case, is a constant. It's always the same. So it would look like this. It would be a straight horizontal line. We can use plots to determine the order of a reaction. So if you're given a bunch of data, let's say you're given, again, concentration and time, and you get a bunch of data, you can try plotting the data and seeing what order it follows based on what creates a straight line plot. So if the most likely order is always first order. So I could take this and I could use Excel and determine the log of A. And then I could plot this as my X and this is my Y. And if I end up with a straight line, negative slope, then I have a first order reaction, right? This is the log of the concentration of A versus time. Then it's first order. I could do the same thing. If it's not a straight line, then I could look at whether it is second order. And there I would plot 1 over A versus time. And if that's a straight line with a positive slope, then I have a second order reaction. And of course it's possible, although less likely, I could have a zeroth order, and that would be where I plot the concentration in time, and I get a straight line with a negative slope. Okay, so sometimes this is the approach that is used to find the rate order of a reaction, and all of these methods also reveal what K is, because K is going to be either the slope or the negative of the slope. This is the back page of your packet, because it's a nice little cheat sheet that summarizes the differences between the rate laws and also shows, or the different rate orders, and also shows what their plots would look like. And knowing these can be valuable in answering a variety of questions. So I would make sure you were familiar with these equations and knew which were on your equation sheet and which ones you can figure out based on what's in the equation sheet. The equation sheet does not tell you which ones are which order, so you have to be able to look at that information and know what it's for. Okay, so we're going to stop right there.